All right, so this is the first problem. You know, we just needed to set up an integral for the length of this ellipse. You don't need to waste time to evaluate the integral. Sometimes it's impossible. Okay? So read the question carefully. So set up an integral for the length and use this is the original formula. Then then all you have to do is just write down the details. T is from 0 to 2 pi, and the derivative of x with respect to t is going to be -2 sine t squared and plus dy is 4 cosine t squared and dt. That's it. So if you understand the problem, it's simple, just one integral. That's it. Takes only a few seconds to write down the answer. Now for the second problem, sketch the graph and find the area of the region enclosed by this curve. So this is a graph. Sketch the graph. Okay, with I equals 3 plus 2 cosine theta. Then find the area of the region enclosed by this polar curve. Okay. All right. Now we have to, we should know before we sketch the graph how the graph look like. Okay. There are, in general, you have a plus b cosine theta or I equals a plus b sine theta. Doesn't matter which one you use. Okay. So the graph depends on the relative value of a and b. Okay. So if a is absolute over a, over b is greater than 1, and then the graph looks like that, or rotated. Okay. So I just give you a typical example. You know, it's not necessarily in that position, but there is no self-intersection. Okay. So if a or b equals 1, then it's possible it's going to be like that. Okay. So that's this cusp of the curve attached to the origin. This is an x-axis. That's y-axis. Okay. Now, if a or b less than 1, then the graph looks like that. Oh, sorry. Yeah, I'm going to draw the graph. No, that's too big. Yeah, to be like that. Yeah, something like that. Okay, so it's very hard to talk about area of this region enclosed by this curve because you don't because it has self-intersection. But look at our example. Look at our example. I equals 3 plus 2 cosine theta. And this one clearly, it's always positive. I is always positive. Now, for the above 3 pictures, right? The last picture tells you R could be negative, okay? R could be negative somewhere. But the first one is I is always have the same sign. But look at this one, and then notice that I is between, the largest possible value for I is going to be 3 plus 2, which is 5. The smallest value for this is going to be 1. Okay, so I is always between 1 and 3. So this will, the picture will be like the above one, the first one. Okay, so it will increase. All you have to do is just, yeah, let's draw the picture here. Okay. So when theta equals, just look at the value, theta equals 0, I equals 5. Now this is longest one, right? When theta equals pi over 2, I equals 3. When theta equals pi, I equals 1. That's the shortest, right? When theta equals 3 pi over 2, I is going to be 3 again. Okay. Then finally, when theta equals 2 pi, I equals 5. So the picture is going to be like that. Okay. Yeah, it's so you get a picture, and here's going to be, you know, in the XY coordinate system, this will be -1 and 5. So that's enough when you draw the picture. Okay. Now, write down the formula for the area. The area is the integral from 0 to 2 pi. I think it's r squared, the theta. Okay. So you write down that formula first before you put the details in. It's going to be 1/2, and I is going to be 3 plus 2 cosine theta d theta. Right, so, and you can multiply this out, it's 9 plus 3 times 2 times 2, 12 cosine theta, and plus 4 cosine square theta d theta. I think the integral for cosine theta is going to be 0 because it's a periodic function from 0 to 2 pi, and has an equal area with negative sign, you know, positive, negative cancel out. Okay, so you don't even worry about it. And cosine square theta, you have to convert it to, yeah, cosine square theta is going to be, remember, you know, sine square theta is going to be, see, here's a formula, cosine 2 theta equals cosine square theta minus sine square theta. So if you want to go to cosine square theta, then 2 minus. So you will be at 2 divided by, so this will be cosine 2 theta plus 1 divided by 2, and it cancels out 2, and that is what you get. Okay. Again, the antiderivative of 9 is 9 theta, and the cosine, I think this part is always 0, and that part will be 0, the integral, so don't worry about that. And you get 2, yeah, 2 plus, it's 11 actually, just 11 theta. Yeah, it's 11 plus the left, so 11 theta integral from 0 to 2 pi, and 11 pi. So that's going to be the answer. Okay. So the problem on the test, you know, still about some polar equations, and you have to learn how to sketch this graph. If the polar equation is in this form, a plus b cosine theta, and you should know there are 3 types of curves. Okay, and I think it's more precise picture should be, let's we show that it's going to be, it's not a curved in. Okay, it's going to be like that. All right. Yeah. But anyway, there's 3 versions. Okay. Now, for rest of them problems will be power series, infinite series, power series, Taylor series. It's from section 11, chapter 11. Okay, so the third problem, determine whether the series is convergent or divergent. Okay. Yeah, you look at this problem. First of all, to check whether this series, this sequence, this series, the nth term conventional zero or not. Now, sometimes it is written in a different form. It is written in that form, 3n plus 4n, maybe 3 to the power n, you know, depend. Okay. So I make a simple observation. I find out this is a convergent. Okay. And I'm going to use a comparison test to prove it's convergent. So this is a AN, okay? AN is going to be, okay? I drop the positive one, so I get 4 over 3 to the n, and that's going to be 3 over 4 to the power n, that to the n. So you get the geometric series, and with r less than 1, 3 over 4, right? So we know that this is convergent by the geometric series, geometric. Right? So we know that. Then this is the convergent by the comparison test. So this is a complete solution. Okay? I gave a 4 credits to complete the solution, not to the answer, convergent not, because you have to prove your statement. Okay? You cannot just say it's convergent, that's it, or put some incomplete argument to there. Okay. So is there any other way to discuss, to prove it's convergent? I don't think so. Even you see the exponential function here, but you cannot apply the nth root test to prove it's convergent directly. Okay. The reason is, how do you find the nth root of this? How do you simplify it, right? So I don't think it's any way you can solve the problem. There are some problems you can use a different method, but this one you can only use the comparison test. Maybe limited comparison test works, but you have to find the limit. Okay, use the same B. Okay, A and B and maybe the ratio converging to 1. Okay, but that's it. You know, limited comparison comparison test is in the same category. Okay. 4. All right. This one, clearly it's convergent. Okay. Now, if I do not ask you whether it's absolute convergent or condition convergent, you don't need to say that. You just say convergent or divergent. Okay. But you have to prove it. I can tell you that this is actually absolute convergent, but I don't need to say that because it's not asked to discuss this kind of convergence. You just needed to say it's convergent and prove it. Now, this particular problem, I can show that it's convergent, not only convergent, I can even find its value. Okay, so the first method is, and you can just modify these two n factorial negative 2 to the power n. And this is, you remember, if only the first term is missing, so it's going to be e to the negative 2 minus 1. You know why? Okay, using the following fact n starts from 0, n factorial x to the n is going to be always convergent to e to the x. We already proved that. You can use this fact. Okay? The radius of convergence of this Taylor series is going to be infinity for any x. So in particular for -2, when x equals -2, then it's convergent to e to the -2, but the y e to the -2 -1, because this series there is an addition term there. The first term is 1, but above series n starts from 1. You know, this starts from 0. Okay, so the first term is actually is 0. So this is going to be 1 plus, right? So that's the reason if it starts from 1, n starts from 1, then you have to move 1 to the other side, you get e to the negative. Okay, so that is a complete argument. The second method, when you see n factorial, right? What is the best way to do? Ratio test. You cannot use a row test. Okay, you think I'm all the possible method, ratio test, you know, it's convergent, right? Integral test, no, that's not working. Okay, and then what is left? The comparison test, right? But you have to compare with some nice ones. It's already a nice one. Okay, so it's ratio test is better, right? So ratio test. Okay, so ratio test, here's our n is going to be negative to this, right? And 2 to the n factorial. But you have to learn all those tests. You cannot just always use a one test to do all the problems. Does not work. Okay, I was grading the makeup quizzes in my office because I did not grade the other quizzes. And I find one students always use a ratio test for all the problems. Okay, that does not work. Okay, so the ratio test, you take up a true value of this. Okay, this is going to be negative sign is gone. So 2 to the n plus 1. And you have to find the limit. You cannot just leave that if you use a ratio test. You have to simplify. Okay, after you simplify, then you have to show me how to get the limit. Okay, so this will be 2 to the n plus 1 over 2 to the n. And this is n factorial n plus 1 factorial, right? Then you continue to simplify in order to find the limit. It's just 2. And this is just 1 over n, 1 over 1 plus n. And clearly this can be 0 as n approaches infinity. Okay, so the limit L is going to be 0 less than 1. Now what you can say about the ratio test? By the ratio test, this one is convergent. Okay, so that means the series is absolute convergent, i.e., this series is absolute convergent. It's not alternate series. Okay, this is absolutely convergent. Oh, convergent is absolute convergent. Okay, so absolute convergent, then we know that it's convergent, but you already get more than what you need. Okay? Of course, in particular, it is convergent. Okay, so we get more than we need. It's absolute convergent. Okay, so that's it. So this is a complete argument. You can also skip that part by the ratio test. It's convergent. That's it. That's fine. Right? But the detailed ratio test says that when L is greater than 1, it is absolute convergent. When L is smaller than 1, when L is greater than 1, it is divergent. Okay, there is no absolute divergent, just divergent. It's divergent is divergent. Okay. Okay, so that's. I don't see any other methods can use for them, for that problem. All right, This one, it also has two different methods to solve it. Okay, it is convergent by direct argument by the definition of convergence of a series. Okay, so how do I do that? The first method, you look at the partial sum. Okay, you look at this partial sum. You know, when this series is convergent, right? By definition, the partial sum as a sequence convergent. Okay, but when you write down the details, it is going to be the first term is 1 over 1 minus 2, the second term 1 over 2 minus 1 over 3, and the last term is 1 over n minus 1. Well, when you remove the parentheses, all the terms in the middle cancel out. Okay, when you remove, because negative 1/2, positive 1/2, negative 3, 1/3 plus positive. So it's going to be 1 over 1 minus 1. Now, clearly, this approaches 1 as n approaches infinity. Okay? Yes. So this just coming, this, you know, the origin definition of the convergence for the series. We don't use the tests, you know. Those tests we already proved that, but we use the origin definition. It's like a formula, right? But the origin definition for the convergence says that the series is convergent if only if the sum of the first n terms is called partial sum, convergent to a number. Okay, so it's convergent to 1. So I not only prove it's convergent, it is convergent to 1. So this implies, right? So i.e. this series is not only convergent, I know the value. Okay, okay, it is convergent. Okay, it is convergent to 1. You can get all the origin information. The second method is trying to use, I don't want to know, it's sometimes difficult to find the value even. So I modify, this series, the series is going to be, right, 1 over n minus 1 over 1. But you can combine those two terms into 1. So what you get here is going to be, here's n times n plus 1 over n plus 1 minus n, which is just 1. So now it's clearly it's convergent. Why? The denominator of the nth term is going to be almost n squared, n times n plus 1. So this is my an. I can use a limit test. I can use a limit comparison test. I can use a comparison test. So I use a comparison test. N is n plus 1, which is less than or equal to n times n, right? And which is 1 over n squared. That's my Bn. So I get P series. Okay. So this Bn is convergent by the P series test. We already proved that, right? Was P equals 2. Okay. So this implies is convergent by the comparison test, right? Right? I don't see any other tests can be used here. You cannot use a ratio test. Yeah, some students will always use a ratio test to do the problem. The ratio test, the limit is going to be 1. It doesn't work. The ratio test only is used for the nth term containing n factorial or the exponential function. Don't use that to any series like in this type of one. Okay. And for example, this is the number 6. Okay. you have to use an integral test to check the convergence. If I say use an integral test, you have to use the integral test. Use the integral test to determine whether the series is convergent or divergent. Right? To me, I think it's clear it's going to be divergent. Okay. Now you can even look at the general case. Okay, when you have, I discussed that before in the class. 1 over n times, this is not nth root. Okay, this is a square root of natural log n. All right. We have to use the integral test. All right. So here, the an is going to be n square root of natural log n. So the corresponding function should be recorded, right? Then n equals f of n. Okay. In order to use integral test, you have to check that f of x is positive, right? Second, f of x decreasing. I think a decreasing is obvious because it's a determinism. So then we can use the integral test because those two conditions are satisfied. All right, so we have to look at the integral from 2 to infinity. Okay, when you see the integral of that, how do you solve the problem? Use a substitution. Okay, so use a substitution. Let u to be natural log x, right? And du equals 1 over x dx. So the integral becomes, when x equals 2, it's natural log 2. When x goes to infinity, u approaches infinity, okay? And this is going to be square root u, and that's just du, okay? And clearly, this is going to be divergent because the p is 1 negative 1/2, okay? So you get natural log 2, u to the negative 1/2 du. The entire derivative will be 2 u to the 1/2, okay? And that clearly is infinite, it's divergent, okay? So this series is divergent, so it implies this series is divergent, okay? All right. So this is the only method you can use to prove it's divergent because I specify the integral test. So there is a question ask you whether it's absolute convergent or condition convergent or divergent. Okay, so you have a series. Yes, this is n. Okay, so my question is absolute convergent, condition convergent, or divergent? So that's the question. And you have to prove your claim. If it's absolute convergent, you have to prove that. If it is condition convergent, You have to prove it. When I make this simple observation, I see that n over n squared minus 1 is almost equal to n over n squared is almost, it's going to be 1 over n. So clearly, this is not going to be absolute convergent, right? This is a conditionally convergent. If it's like alternating series, right? Because there is some sign there. So I begin with, I have to prove it's not absolute convergent, okay? Then, and it's convergent. Then I say it's condition convergent. So how to prove it's condition convergent? You have to prove that it's not absolute convergent. You have to prove that it's convergent. Then it's condition convergent. Okay. So yeah, by simple observation, this implies if I remove the negative sign, I will end up with a harmonic series, almost, right? It's 1 over n, so it's divergent. Okay. Yeah. So this, yeah, I'm going to call it, yeah. So this is, I'm going to use, call this one is n, this one is b, right? So clearly, the limit of n over bn equals 1. I'm not going to check that. That's where, how do I get a bn? So I drop a negative 1, I simplify, then I get a bn. So the limit is always equal 1. Okay? So we know that sigma of bn, and start from 2 to infinity, is going to be infinity because it's harmonic series. You can say that by the P series test, okay, with P equals 1. Okay, so this implies this is divergent, okay, by the limit comparison test. So what is n? N is a series without negative sign. So this implies is not absolutely convergent. At least I can show that, right? It's not absolutely convergent because when I remove the negative sign, it is divergent. Is it convergent? I think so, because it is almost like a negative 1 to the power n and 1 over n. So I claim, think about it, right? This is not absolute convergent, but is it convergent? Okay. Right? So the question is it convergent? Yeah, this is alternating series, right? So to prove an alternating series test, alternating series is convergent, you have to verify some conditions, right? So here, n equals n over n squared minus 1. What I have to prove that? It's positive, it's of course. It's decreasing, it's not easy to see. It's decreasing to 0, it's obvious, because why? The numerator is n, the denominator n squared minus 1. So it's clear that, yeah, but you have to list all of this condition. It's okay, it's obvious, right? Second, right? N decreasing question. Third, this goes to 0, obvious. I'm going to only verify the second. You can put this obvious, right? Obvious. In general, just the term in the middle, yeah, decreasing is not easy to verify, okay? And because there's numerator and denominator there, okay? How to do this? I use f of x equals x over x squared minus 1. right? As long as this function is decreasing, then the corresponding, right, let, then there's a corresponding series, a corresponding sequence is decreasing, right? So I just need to prove the function is decreasing. Then I differentiate, I got x squared minus 1 z squared, right? And derivative of x is 1 minus x times the derivative of x squared minus 1 is 2x. So I get -1 minus x squared. It's always negative, as long as it's defined. So that means f of x decreasing on the interval from 2 to infinity. Step, okay? This implies n decreasing for n greater than or equal to, okay? So then, and therefore, this implies a series and -1 to the n is convergent by the alternating series test. All right. All right. Final conclusion is this series is conditionally convergent. Okay. By definition, what is condition convergent? It is not absolute convergent, it is convergent, but it's convergent. Okay. Find the radius of convergence for the series, for this power series. Okay, so this is a power series, and you can use either method, limit ratio test or the row test. Okay, so the first method use a ratio test. So this is your n, right? And the ratio test. If I see n factorial, you cannot use a load test. If just n square and cube, I can use a load test too. Okay, so it's going to be 1 over n plus 1 square and absolute of x n plus 1 and 1 over n square absolute x to 1. So after simplified, you will get n square over n plus 1 square absolute x. Okay. Yeah, x cancels out. Now, even this, if you divide by n, the numerator and denominator, you get something like that. So the limit is just x. Now, clearly, when this is convergent, only when x is less than 1, absolute x. So clearly, this series is convergent. Yeah. Is absolutely convergent for this, and the divergent for x greater than 1. So r equals 1 is the radius convergence. Okay, and by the ratio test, I have to say that. Okay, so I don't need to say anything about when absolute x equals 1, because I just want to find the radius convergence. If I ask you to find the interval of convergence, you have to look at 2 endpoints. Okay, so we conclude that r equals 1. Okay, then. Now the second method use a ratio test, and then you have to take a look at absolute nth root of absolute n. and this is going to be n squared, right? Now, after you simplify it, and how do you deal with the denominator? The denominator is just nth root of n squared. And we already know the limit is going to be 1 of this denominator. Okay? I have to using the fact as this is fact that I've said several times, and I already gave a proof. Okay? So using this fact. So the same idea, you can see that this series is convergent, right? And by the root test. So it is clear that this one is absolutely convergent for x less than 1, divergent for absolute x greater than 1. Okay? Therefore, yeah, you have to set that by the root test. Okay? So conclusion is the radius of convergence is 1. Right? So you can use any of this test to prove that. Okay? Yeah, to get the radius convergence. Okay, the radius convergence cannot be larger than 1 because when absolute x greater than 1 is divergent already. Can you evaluate? Can you express this series as an elementary function? Maybe, but we're not going to do it here. The next problem we're going to do is to find the Taylor series for the function f of x equals fx equals natural log 4 minus 3x at a equals 1. Now we have to assume that f has a power series. Don't need to evaluate. This is a section 11.9. You know, you have to memorize a bunch of formulas in this section. Let me go back to chapter. Which chapter? 1110. Yeah, 1110. So there are 3 table 1, page 808. Right? Yeah. So page 808. Okay. Table 1. So I see there's natural log of x there, right? So let's recall the formula. So this is going to be n minus 1, okay, x to the power n of n. And the radius of convergence is 1, so it's convergent when x is less than 1. Okay. So this is known fact. You don't need to prove it. You just use it. Okay. I think, okay, there are a couple ways to find the Taylor series. If you're able to find all the derivatives, the first method, use the definition of Taylor series. Okay, the definition of Taylor series says that, so the first method, using the definition of Taylor series. Okay, so that is going to be okay. All you have to do is to find the nth order derivative of this function. You can do that. It takes time. So f of x equals natural log of 4 minus 3x, right? And you have to define again, you know, the first derivative, it's going to be what? It's just go to the denominator, right? So 4 minus 3x to the negative 1, and then put the negative 3 here, right? It's not too bad if you do that, okay? The second derivative, and then it's going to be negative 4 minus 3x to the negative 2. Then I get another negative 3, so it's negative 3 squared. Okay, and you have to find a pattern to get a general formula. The third derivative, and then it's negative 1 here, then I get a negative 2, right? 4 minus 3x to the negative 3. Then I get another negative 3, so negative 2. So I guess now I already get enough information. I get the pattern. Okay, I get the negative 1, negative 2, all the way, negative n minus 1. And here 4 minus 3x to the negative n, negative 3 to the power n. So this is a general formula. Okay, and how many terms here? I have 1, 2, 3, that's n minus 1, right? So I'm going to collect them. It's negative sign. This is going to be n minus 1 terms. And then this is n minus 1 factorial. And this will be 4 minus 3x to the negative n, negative 3 to the power n. And because negative 3, there's negative 1 to the end there, right? So you can get rid of the negative sign, and I get okay. I have a negative 1 to the power n and negative 1 to the power n minus 1. So combine, I get a negative 1. Okay. So the value at 1, I get 4 minus 3 to 1, that's just only 1. Okay, so after I simplified, okay, so we are looking for the, so this is it, right? So the Taylor series is going to be n factorial, negative n minus 1 factorial, and the 3 to the n, and the x minus 1 to the n. Okay, then you have to simplify a little bit. Okay, so you get a series. That's only the candidate for the power series representation of the original function. The Taylor's work, why it's called Taylor series? Taylor showed that this will be convergent to the function. He has a general idea, show too. Okay, then it becomes, that's why it's called Taylor series. That's Taylor's contribution. But we just want to find the Taylor series. That's the Taylor series. It's just only the candidate for the power series representation of that function around the 1, at the 1. Okay. So, but that's all you needed to get. You don't need to prove it's convergent to the function. Okay. You don't need to even determine the radius of convergence. But that's just candidate. Okay. All right, but that is that's used. It takes lots of time to do, right? You see that you find out all the derivatives, and then then you get a Taylor series. Okay, so the second method is we use the known result. Okay, we know that just find the power series representation for the function. If you find the power series representation for the function, then that is Taylor series by that theorem. Okay. Find the power series representation in the form Cn x minus 1n for the function equals natural log of 4 minus 3x. Okay. And this power series, this is Taylor series. This is the Taylor series, if it exists. Okay. Okay. And there is a theorem guarantees that, okay, in the book. This is the Taylor series that went by the theorem. I have to mention because there's no name for the theorems. All right, by theorem 5 page 800. Okay, the very top one. All right, so but let's use that. Let's find the terrace power series representation. So this problem can be changed to the problem like find the power series representation. Okay, instead ask you to find the Taylor series. All right, so what I'm going to do is we are going to let x to be x minus 1 plus 1. That's a typical notation. That's u plus 1. Okay, where u equals x minus 1. Okay, then f of x, remember it's a 4 minus 3x, right? This is going to be 4 minus 3 u plus 1. After simplifying, 4 minus 3 minus 3, right? I got 1 minus 3u. So I'm going to use the above formula on page 808. Right? The formula says that it is going to, so this is my x. Okay, this is the x part. So according to the formula, it is going to be n start from 1, negative n minus 1. I remember this is a n, and this should be 3u to the power n. Okay, negative 3u is going to be less than 1. Yeah, this holds. Okay, by the above fact, right? Above fact says this is a formula. Go back, right? I already mentioned that earlier. Natural log 1 plus x equals negative 1 to the n minus 1 and x to the power n, right? This holds for absolute x less than 1. So here, in the place of x, it is negative 3u, okay? So you simplify a little bit, and the negative 3 to the power, negative 1 to the power n is negative. So it's actually negative, and 3 to the n, and u to the n's power. And this is going to be less than 1/3, okay? So let's replace u by x by x minus 1 to the power n, and here x minus 1 is 1/3. All right, so we find the power series representation for the function. Not only that, we determine the radius of convergence for this power series, which is 1/3. Okay, and then this should be the Taylor series, and this match was the same one we got. Okay, it is. Then you can say that it is the Taylor series. Okay, f of x. Okay, so that is that is us, okay? Because at the very beginning, the function is equal to this series. This is power series representation. You find the power series representation for the function, and you know the radius of convergence, and you get the problem. All right, I'm going to take 1 minute to discuss the last problem. It's the same problem, f of x equals 5 minus 4x. Okay? Find the power series representation. Okay, in the form, okay, in this form. So the same idea, you quickly get x equals x minus 1 plus 1, which is u plus 1. Then the function is going to be 5 minus 4 and u plus 1. And I get 5 minus 4u minus 4. And that is going to be 1 minus 4u. And I know there's another formula in the book, and this should be equal to, and start from 0 and negative, not negative, just 4 u to the power n. And this holds when absolute 4 is less than 1. Okay? Then finally, it's going to be 4n to the u to the n, and here it will be 1/4. Okay? And then finally, you get, okay, and here x minus 1 less than 1. Okay. So this is a power series representation for the above function. The code here, we're using the formula on page 808. Okay. So that's it.